In this video, we're going to go over some of the basics of primary cell removal. This will be removing cells or separating the cells from the broth out of a fermentation, and we'll primarily focus on centrifuges and centrifugation. So if you remember in our downstream recovery workflow, we end up at the end of the fermentation with a whole broth, which is the spent media and the cells, and we're looking to first do a size separation to separate the cells that are in the broth from the liquid. And this would be the primary cell removal step. And depending on where your product is, if it's inside the cells, is the cells, or outside of the cells, it would depend on which fraction you would keep. You would either keep the broth or you would keep the cells. But in either case, there are three primary ways you would do this separation based off size: filtration, microfiltration, or centrifugation. There are some practical differences when you're looking at comparing filtration, microfiltration, and centrifugation. If the cell is the product, you really want to be doing microfiltration or centrifugation. That would be the same thing for intracellular product. If the broth is the product, filtration can be a little bit better. Filtration has a relatively low cost. It can recover virtually all the broth, but it's pretty hard to do sterilely, and you can have contaminants ending up in the broth or filtrate. Microfiltration has become a standard in the pharmaceutical industry. It can be done sterilely, and you can retain 100% of the cells. It is a little more expensive than centrifugation. You basically buy these pre-sterilized filtration cassettes. It cannot remove all the water or extracellular contaminants, and you do lose some of the extracellular product with the cells if your product is in the broth. Centrifugation is a little less pricey than microfiltration. It can be done sterilely. It cannot remove all the water. It cannot remove all the extracellular contaminants. And just like microfiltration, you can lose some of the extracellular product with the cells if your product is in the broth. We will focus primarily on centrifugation, and there are two types of centrifuges that are primarily used. And in the pharmaceutical industry, we almost exclusively would use a disc stacked centrifuge. So we'll focus mostly on this. A tubular centrifuge is what it sounds like. It's basically a tube that spins, and as the broth is pumped upward in this direction, as this is spinning, particles are sedimented against the wall. In a disc stacked centrifuge, you have feed coming into the centrifuge. You have discs to help separate the cells and keep them separate from the broth. This is spinning. The cells accumulate at the sides here, and there's a periodic discharge that happens where the cell concentrated slurry comes out of the disc stack centrifuge, and then clarified broth leaves. If you haven't seen the video that's also posted on how these disc stack centrifuges work, I would recommend taking a break and looking at that video now. In either event, centrifugation occurs through sedimentation, and that can be tracked by looking at Stokes' law. So the sedimentation velocity, UG, is a function of the density of the particle that you're trying to separate, which in this case would be cells, the density of the liquid that you're separating the cells from, the viscosity of the liquid, the particle diameter, and the acceleration. In a centrifuge, the acceleration is a function of the angular velocity omega of the bowl and the radius of the drum. So we replace this g with omega squared r. Or you can have the g force z relating the angular velocity to the gravitational acceleration. So we can define d max as the maximal particle size ending up in the clarified broth or supernatant, meaning we don't want any particles bigger than that to end up in the supernatant. And so basically if this would be the size of a cell, for example, if you want to have 100% recovery of the cells, right? And in this case, we can have the particle, which would be biomass, the density of the biomass, the density of the media, viscosity of the media, the particle size, which in this case would be the cell size, and the gravitational acceleration. So in most cases, you can estimate the density of microbial cells to be a little bit more than water. For this analysis, we'll consider that the media is primarily water and has a density of water, although that may be quite different. We estimate the E. coli radius at 0.5 microns. It would be 2 microns for yeast, and then we have the gravitational acceleration. And then the viscosity of water at 20 degrees C we can plug in. And this basically gives us two sedimentation velocities needed for complete clarification or removal of two primary cell types, E. coli and yeast, from the broth. So in the case of E. coli, when we have the E. coli size, we have 6.8 times 10 to the negative 9th meters per second, and in yeast it's 1.1 basically times 10 to the negative 7th meters per second. So these would be the needed mu0 required for complete broth clarification. You could do the same analysis with any other type of cell. So we know what the sedimentation velocity would need to be, and now we need to understand how we design a centrifuge to achieve that. And so the sigma factor is a critical characteristic of centrifuges, and it relates the flow rate, so this would be how much broth goes into the system, to the sedimentation velocity that you can achieve. And it helps describe the performance of a continuous or semi-continuous centrifuge. So you have the volumetric flow rate, this would be liters per minute, liters per hour, liters per time, and the terminal velocity, which would be equivalent in our case to the terminal velocity we calculated for the different cell types. So if two centrifuges perform with equal effectiveness, then the ratio of the flow rate to the sigma factors are equal. Right? So these would be equally effective centrifuges. For operations at constant centrifuge speeds, solids recovery is inversely proportional to flow rate. And this is actually pretty important, and we'll go through an example of that. So how do we estimate the sigma factor for a centrifuge? We can actually come up with some pretty specific equations in the case of a tubular or disc stack centrifuge to calculate the sigma factor. So in the case of a tubular centrifuge, R2 would be the radius of the tube, R1 would be the radius of the liquid surface, R2, R1. We have B is the length of the tubular centrifuge, and then omega would be the angular acceleration, and G the gravitational acceleration. In the case of a disc stack centrifuge, we have R1, R2 would be the outer diameter, R1 would be the the outer radius, and R1 would be the inner radius. The angle would be this angle here. N would be the number of discs in the disc stack centrifuge. And again, omega would be the angular acceleration. And this in cases would be in hertz, and 1 hertz is 9.5 roughly RPM. Due to the need to be able to discharge the solids, they must be fluid, meaning unlike a batch centrifuge that you're probably familiar with in the laboratory, where you have a single tube that you're spinning and the solids are pelleted at the bottom of the tube, you can pour off all of the broth. In a continuous centrifuge or semi-continuous centrifuge, you have to have enough liquid remaining in the cells that you can move them around, you can pump them around. This means that they take some broth or water with them. In general, for fermentation broth, centrifuge solids, which could be in quotations, can be assumed to carry about 35 to 40% water broth with them. So for example, for every 10 grams of dry cell weight separated, you also carry 6 grams or 6 mils of water, so that the total water percent by weight would be 6 divided by 16, which equals about 37% or 40%. And this includes the volume of the cells, right? So in general, you can assume that the volume liquid in the cell fraction is equal to 1.6 times the biomass concentration times the volume of broth, and this would be in milliliters. The volume of the liquid in the cell fraction in liters would be equal to 0.0016 times the biomass concentration times the volume of broth. These are pretty easy calculations. So the volume of the broth times the biomass concentration gives you the absolute biomass in grams. Right? And then we're basically doing this calculation to be able to get the liquid that goes with that biomass. This may have an impact with respect to your yields. So for example, if your product is in the broth, some of that product is going to be separated with the cells and be lost unless you do washing, which we can talk about a little bit later. So this is a good time to take a little bit of a break and just talk about some of the cell sizes and volumes of 2 of the key microbes that you may use in this course. So the bacteria E. coli has a 1 micron diameter, about a 2 micron length. It's about 1 micron cubed of volume per cell. There's about 10 to the 9th cells per mil at OD1. Gram dry cell weight, we've used the correlation coefficient 0.35 in the past. The volume of the cells is roughly 2.5 times 10 to the negative third times the biomass concentration. Yeast is a bigger microbe, so 5 microns in the diameter, 50 micron cubed volume per cell, and less cells per mil, so 2 times 10 to the 7th cells per mil. In the case of yeast, gram dry cell weight is about 1.5 times the optical density. So we'll go through an example problem and then a practice design of a centrifuge. So in this problem, a continuous disc stacked centrifuge is used to separate baker's yeast from fermentation broth at a speed of 5,000 RPM and a broth flow rate of 60 milliliters per minute. 50% of the solids are recovered. So there's two questions. What flow rate would be required to recover 99% of the cells in this if the speed is held constant at 5,000 RPM? And what speed is required to recover 99% of the cells at a flow rate of 60 mils per minute? So tackling the first question first, as we mentioned above that recovery is inversely proportional to feed rate, we can basically do a pretty simple calculation and say that if we have 50% recovery at 60 mils per minute, we need to slow it down to get more recovery. So we would need to slow it down to 30 mils per minute to get 99% recovery, right? And that's pretty much just proportion. So 50 over 99 times 60 equals 30.3, right? If you want to recover more cells, you have to slow down the flow rate, right? Which makes sense. If you speed the flow rate through a continuous system, it has less time for the cells to separate. So basically, if you're increasing this number, the flow rate needs to go down. The next question would be what speed is required to recover 99% of the cells at a flow rate of 60 mils per minute? So first we know that for the same centrifuge, the flow rate over the sigma equals the flow rate over the sigma in two different conditions, or the flow rate ratio equals the sigma ratio. From A, we know that for 99% recovery at a flow rate of 30.3 mils per minute at our 5,000 RPM, right? We just calculated that. So given this flow rate, we're getting 99% recovery. So we know that 30 to 60 equals 0.5, right? That would be sigma 1 to sigma 2. Sigma, we know in a disc stack centrifuge, is a function of the angle, the radius, the number of discs, and the angular acceleration. And because we're using the same centrifuge, none of these parameters are going to change except for how fast we're spinning. So everything else will be the same. So we can relate the speed to sigma. So sigma 1 over sigma 2 equals 0.5 from this calculation, which basically equals omega 1 squared over omega 2 squared. And from that, we know that the initial omega 1, which is 5,000 RPMs, and we can calculate omega 2, which is 7,000 RPM. So if we want to speed the centrifuge flow rate up, right, we want to pump in cells faster and still maintain the high recovery rate, we need to increase the centrifuge speed, basically, or the angular velocity. That should make sense. So for a given centrifuge, there's sort of two key parameters from this, or two key outputs from this. One is that if you are spinning at a constant rate, you need to slow down the flow rate to increase the amount of cells recovered. And if you speed up the flow rate to maintain that same recovery level, you need to increase the centrifuge speed. So there are some basic practical limitations to centrifuge design. So these can be good rules of thumb for what you can actually do with a disc stack centrifuge. Disc stack centrifuges are most commonly used in biotech, and they can run aseptically or they can be sterilized with steam. They do have some constraints, however. So the max solids in the input is 15%, so you can't really put in more than 150 grams cell dry weight of biomass levels into a disc stack centrifuge, meaning otherwise it's just too viscous and too dense for the centrifuge to handle. So this puts a practical cap on the high cell density that you can do and still process in a downstream recovery. The flow rates generally would need to be less than 1,500 liters per minute, which is pretty fast if you think about 1,500 liters per minute. The angular velocity would be less than 10,000 RPMs. You're talking about R2, the outer radius of less than 1 meter, the number of discs 50 to 150, the angle 35 to 50, and the cell density really around 1.05. So now we're going to look at sort of practical design of a centrifuge. So we're starting with a fermentation or bioreactor with liquid. Right? This would be making our product. And we want to do two centrifugation steps. One would be first to concentrate the cells. We're going to then add liquid to wash the cells. and then we're going to centrifuge it again. So we're doing 2 centrifugation steps to be able to clarify the broth and wash the cells to remove any contaminants that are from the broth. So what's important when you're designing these unit operations is understanding what's going out of one and into the other. And so this would be for all downstream processes. You'd be able to estimate not only what's coming into these streams or coming out of these streams, but the flow rates as well. So in the case of a bioreactor or fermentation, this would be a batch. So we would have a particular volume of fermentation broth at a given concentration that we need to centrifuge. Right? So if we want to do 2 centrifugations, let's say an hour each, right? So we want to do one step, do an hour, resuspend the cells, do another step in another hour. So within a morning, you could get the clarification done. That would be sort of on time with a contract manufacturing organization that would do pharma. Then we would need to have the flow rate for this centrifuge would be the volume that comes out of the bioreactor divided by an hour in this case. So the first step in figuring out what our centrifuge needs to do is to figure out what the maximal velocity or terminal sedimentation velocity we need for this centrifuge. And so if we're doing E. coli, we calculated that previously, it would be 6.8 times 10 to the negative 9th meters per second. For yeast, it would be 1.08. You could calculate this again for CHO cells or mammalian cells, right? So we need to know the the sedimentation velocity. And we also need to know the flow rate. And we calculated the flow rate beforehand, just now, based off the volume of the fermentation broth that we want to clarify and the time we have to do the centrifugation. So in general, in a good manufacturing process, CMO type facility, you would maybe run the centrifuges on average 2 to 6 hours a day. People don't tend to run these things overnight. And that gives a total weekly fermentation potential maximum flow rate of or time of 30 hours, right? We just said that we're going to try to do this in an hour, right? So that would give you the Q could be calculated as the volume of the fermentation broth divided by an hour. In a large scale process, you're talking about like an industrial fermentation for a chemical. Centrifuges have about 80% uptime annually per year, and so you can calculate the total time divided by the total annual fermentation volume. So once you have an estimate of the flow rate you need and you know the sedimentation velocity you need to achieve based off of what your cell type is, you can calculate the sigma. Right? And then we can design our centrifuge based off of that sigma. So the sigma can be as a function of the centrifuge design, which would be the outer radius, inner radius, the number of discs, how fast you're going to spin the centrifuge, and the angle. And for most high volume bioprocess applications, you can assume theta would be 45 degrees and n could be 50. So you can kind of just assume that you're going to be able to get an off-the-shelf centrifuge that's 45 and 50 of a given size, and that can give you a calculation of how fast this needs to spin. So cost considerations for this, so 1,000 liter per minute maximum capacity centrifuge can be estimated about $500,000 in terms of equipment costs, and the operating costs are really just power consumption as well as sterilization, but we'll talk about that in another lecture. So the power consumption of a disc stack centrifuge is, in this range is probably about 2 to 10 kilowatts. You do need to calculate, however, that you will lose product that goes with your cells. So this will affect yield when you're doing your calculations for your downstream process. So if you remember from our downstream overview lecture, and if you haven't reviewed that, I would take a step now and review that again. We have 3 major metrics that talk about how good each of the unit operations in our downstream purification are, including centrifugation. So delta would be the concentration factor, alpha the separation factor, and percent yield. So yield is simply the product that you get out of the step, the product you put into the step. Delta is the concentration after over the concentration inside that goes into the step, and then alpha would be the concentration of the product over the concentration of the contaminants. The product to contaminant ratio that comes out over the product to contaminant ratio that goes in. And for centrifugation, when we're considering biomass or cells as the contaminant, it's pretty easy to calculate these parameters. So if the product is in the cells or is the cells, then you can basically estimate alpha, delta, and percent yield relatively quickly. So percent yield is the percent recovered solids, and usually you design your centrifuges to get 100% yield effectively. You do get water with the solids, and so that's where you have a delta, where you have the percent recovered solids over the amount of water that comes with them, basically. This X would be the biomass concentration. And alpha equals delta when considering the broth components as contaminants, right? So the cells will be the product, the broth will be the contaminants in this case, or the byproducts, and so alpha would equal delta. If the product is in the broth, then the percent yield is basically a function of the amount of broth that's lost in the biomass, which is this amount. And so it'd be 1 minus this fraction, again, where x is the biomass level. Delta equals 1. You virtually get rid of 100% of the cells. You lose some of the broth, but you get rid of the cells. So you have a concentration factor of 1 and an alpha of affinity. This is when considering the cells as the contaminant, you have complete separation or complete purification of your broth away from your cells. So with that, we will end our discussion on centrifugation. Hopefully this was useful.